here we go. This is how you do this problem. Now let me read it again. Number 18. A 50-foot wire runs from the roof of a building to the top of a 10-foot pole that is 14 feet across the street. How much taller would the pole have to be if the street were now 16 feet wider and the wire remained the same length? Now, notice there's no answer choices here. This is usually a multiple choice question, but what I'm trying to do is show you exactly how you would actually be able to do this problem systematically, algebraically. So watch. It's talking about a building. Here's my building. I don't want to get too detailed. Here's my building. Here's my pole. And the pole is 14 feet across the street. Okay? The pole itself is 10 feet tall. And I know that the wire going from the top of the building to the 10-foot pole is 50 feet. This is me just labeling everything based on the original sentence. Okay? Now, if I'm looking at this picture, I don't know how tall the building is, but I can dissect this as a geometry problem and see a triangle and a rectangle. Now, for the rectangle, I know if 10 is here, I also have 10 there, 14 is there, I also have 14 at the top. Now, this right triangle, I can figure out the unknown side because of something called the Pythagorean theorem, meaning a squared plus b squared equals c squared. A squared would be either the x or the 14. It can be either one because it's addition in between, so it doesn't matter. The most important one is that the 50, you know, is always the c squared, the hypotenuse. Okay? 14 squared is 196. I can't change x squared, so I'm going to leave it. 50 squared, just like saying 5 squared, would be 25, but with 2 zeros. Subtract the 196 to move it to the other side. I get x squared equals 2304. Do the radical, square root to get rid of the square, I get x equals 48. Which means that this x right here, this portion of the building, is 48 feet. Which now I know this entire building is 58 feet tall because I have the 48 feet from the triangle and the 10 feet from the rectangle, giving me the entire length of this building. Okay? Now they asked me how much it would change if the 14 down here now turns into an additional 16. Or if there's 16 added to it, 14 plus 16 together now means it is 30 feet across the street, which changes my triangle. Instead of 14, 50, and the unknown 48 that we figured out, I'm now doing the same 50, now 30 at the bottom on this right triangle, right? And now here's an unknown again. Now, you can do the a squared plus b squared equals c squared again, but if you know anything about special right triangles, as well as the similar thirds, anytime I see 3, 4, and 5, that combination always stays true. So if there's 3 here, there'll be 4 here, and there'll be 5 here. If I see 3 and 5, that means this is 4. Now obviously this is 30 and 50, but all that means is that this x would be 40 instead of just obviously 4. Okay? So now the length that has changed from the very beginning to the very end went from 48 to 40. That's a difference of 8. So the answer for this question would be 8. Now I can go into more detail about why the answer is 8, but again, you have 20 questions due in 25 minutes. You only have a little over a minute per question. And as you can see, me being an expert in math, it still took me well over a minute and a half to do it. Now, a child who's still in school, trying to be able to answer a question like this, is going to take them a lot longer than a minute and a half. So here's the thing. Is this what they're asking kids to do? Is this what we're subjecting our children to do when they take an SAT? No. SAT questions are a lot, especially math, are a lot more logic and reasoning. Now, if you stay tuned and check out the next segment, you'll be able to understand exactly how I can find out the answer to this question using the answer choices and not even know how to do the Pythagorean theorem or any of this other stuff. Stay tuned. Thanks.